let's see. In the Q&A last night, gave some tips on the homework, and I announced that number 1D would be extra credit. So let me just remind us what that is. So number 1, you're working with the orthodont data, and you're going to use GLS to do correlated data regression. In part D, I'm asking you to take materials from the output of the GLS model fit and use them to manually match the regression estimates and their standard errors, standard deviations. So it takes some effort to do that. The hard part is you need to construct this capital sigma thing. So this is a 108 by 108 covariance matrix. I talked about it last night. Watch the video if you'd like some tips. It's a block diagonal covariance matrix. That's because we have correlation within the 4 observations on the same individual, but no correlation between observations on different individuals. And since the data are organized as chunks of 4, the first 4 rows is individual 1, followed by the next 4 rows for individual 2, and so on, we said that that capital sigma, which is 108 by 108, it's 27 times 4 equals 108, is of this form. We have a 4 by 4 block that is for the covariances on individual 1, and then the same block, because we're assuming the same variance and same correlations apply for all individuals. So we have 27 of these block pieces down the diagonal, and everything else is 0. You can compute sigma 0 under the assumption of compound symmetric correlation. Sigma 0 equals little sigma squared times a correlation matrix, 4 by 4. So 1, 1, 1. 1's down the diagonal of a correlation matrix. And then every off-diagonal piece is equal to rho. From the GLS output, you can get an estimate for sigma, and you can get an estimate for rho. That gives you an estimate of sigma 0, and then sigma hat would be stick that together as a block diagonal form. So I showed code how to do it, but again, it can be extra credit. You don't have to do it. Once you have that estimated covariance matrix, then you can match GLS by doing weighted regression. So GLS is a way to do weighted regression, and when we weight by a covariance matrix, we are doing correlated data regression. This should match GLS exactly, and then this should match GLS exactly. That calculation of variance of beta hat, because beta hat is a vector of coefficients. We have 4 coefficients in this model, beta 0, beta 1, 2, and 3. So the variance of that vector is a 4 by 4 covariance matrix. And if you take the square root of the diagonal elements of that, those are the standard errors or standard deviations of the beta hats. I also gave some tips on how to do the bootstrap with these data. It also takes a little bit of work. Remember that you're sampling individuals. So you randomly generate numbers from 1 to 27 with replacement, and those are the individuals that you need to stack together to create a new data set, bootstrap data set. So for example, if the first individual that's sampled is individual 4, you need to go to the 4th chunk of 4 to get the data for that person. And you start building up the data. You can do it iteratively. I showed code in the Q&A. At the end of the Q&A, the audio cut out for the last couple of minutes, so I thought I would revisit what we were talking about at the very end. There was a question about spaghetti plots and what are they good for, how to use them, how to interpret them. Big picture of spaghetti plots is we're looking at time courses. In the orthodont data, we have 4 time points. So we could draw connected line segments for every individual. So we would have 27 of these line segments. Looks like you dropped a handful of spaghetti on the picture. And basically all we're doing with one of these is trying to get a feel for what's the trend over time. What is the kind of overall pattern over time? What I was saying in the Q&A is that sometimes it's not easy to see it. Like for the SCITS data, you have lots of observations, lots of individuals, and their time courses are really variable, so it's hard to see anything. Another alternative for doing this same task is to do side-by-side box plots. It's a little less messy. So if we were to say, here's the box plot of response at time 1, and here it is for time 2. That gives us similar information. Not exactly the same information, though. By looking at a spaghetti plot, we can also see things like outliers. So we might, if we had this spaghetti plot on the left, and we also had one individual that looked like this, we wouldn't necessarily see that by looking at the box plots. So also think of spaghetti plots as a way to, look at all the individuals. That allows you to look for outlying individuals. So if you're looking at the pattern over time, when you do a longitudinal study, you're often interested in the pattern over time. What is the change in response over time? So a case like where you have some exposure, people come into a trial at time 0 and they're exposed to some medication maybe, and we observe them at multiple time points. We want to know, it's informative, it's useful information to be able to say, is the pattern over time, or what's the nature of it? Maybe it's doing something like this, a spike immediately after exposure and then slowly coming back down to normal. What I'm going to show today is how we can actually model time course patterns. So imagine doing a regression model. Response is equal to some, maybe we have a treatment variable, but we also have time, each individual measured at multiple times. So we could include in our regression model a time coefficient. If I put time in the model like this, then I'm assuming that that the response is linearly related to time. But there's no reason that to expect that there's always going to be a linear time course. The picture bottom left is not a linear time course. So what we're going to consider today is, instead of doing a linear trend in time, what if we allow for there to be some curve, some function of time? It is possible to do that, and it's also possible to make f as flexible or not flexible as you wish, ranging from linear to piecewise linear to curvy. If you have a model like this, then you can do inference on the time course pattern. My estimate of the response at time 3 is plug in the model. And if you have a smooth curve, you can represent arbitrary time courses like that one. So let's look at a couple of new scripts. They're not new to eCampus, we just haven't looked at them yet. Under scripts, I'm going to get one called Piecewise.r. Piecewise.r. And after we look at that one, we're going to look at this one. This is a data set called Menarche, I think. So I'm going to get the script, and then I'll go get the data for this also. Okay. It's being really slow. Let me get the data. Menarche.text contains the data. Okay. Let's look at piecewise.r to see how we can make how we can allow a regression model to have a function of some covariate, some not necessarily linear function of a covariate. Before I go here, notice that, or recall that you can always have a nonlinear pattern in a regression model with something like this. Suppose we had beta 0 and beta 1 time. That's going to assume there's a linear trend, a linear relationship over time. We could also do add, say, time squared. That's a simple way to allow for there to be a curvy relationship in time. This is allowing for a quadratic relationship in time. You could keep increasing the order of the polynomials as well to make it more and more flexible. I'll show you a better way today. Okay, so here is piecewise.r, and we're going to simulate some data. I need a package called splines because we're going to use a tool called a spline to allow for curvy relationships in a model. So let's make sure this is installed. Okay. And I'm going to simulate some data. Let's have a sample size of 100. Let's have a residual standard deviation of 0.25, and I'm just making these numbers up. Let's have a single covariate. We could think of this as time. So I'm going to generate a time covariate. The way I'm getting it is I'm getting uniformly distributed numbers between 0 and 2. And then what I'm going to do down below is simulate from a regression model. But the model is going to allow for, or it's going to have different patterns depending on the value of time. So we're not going to say there's a linear relationship in time. We are going to allow for there to be a relationship like this. So x and y. Instead of saying there's a linear relationship on average between x and y, I'm going to say there's a piecewise linear relationship. So I recently collaborated on a research project with a guy who's in the Navy, and he was studying mental health utilization among service members over periods of deployment. So when you're in the Navy and you go out, you spend some of your time on aircraft carriers, say, they rotate you through, sometimes you're at home, sometimes you're preparing to go out, and sometimes you're out. So the interest was, let's look at spouses of family or of service members and their how much they're using mental health facilities. So like you might imagine when your husband goes off or your wife goes off to be on an aircraft carrier for 6 months and you're stuck at home with kids, maybe your depression levels go up and that kind of thing. And then when they come home, they go down. So the interest was, let's look at temporal patterns by deployment status. And we specifically wanted to allow for a piecewise linear pattern. So I didn't necessarily want a quadratic curve. We specifically wanted a piecewise linear. So how can you do that? How can you have a model that allows for there to be one line there and a different line there? The key technical issue is making sure that we have these two lines that join up at the boundaries. So I'm going to simulate some data that's kind of like that. We're going to have times that go between 0 and 2, and for times between 0 and 1, there's going to be one regression model, one linear trend, and for times greater than 1, there's a different one. So I pulled these coefficients out of the air. Let's say that before time 1, the pattern is intercept 0, slope 1. And after time 1, the intercept is 3 with a slope of -2. In practice, you don't know these things. We're playing pretend. We're doing a simulation. So we're going to create some data like this, and then we're going to see how to fit a model to data like this. So let me simulate the data and show us what we have. Okay, so here are your time course data, and you can see that there's this piecewise linear pattern underlying it. There's this pattern to the left of 1, and then it changes to a steeper declining pattern after 1. All right, so the function we're going to meet now is this BS, which is, BS stands for B splines. So these are splines. Splines are, roughly speaking, a spline is created by picking some locations to have so-called knots. So I'm going to call these knots. These are locations where in between them we're going to have some curvy relationship. And at the knots, we have a requirement that the curvy relationships join up. So a spline would allow for there to be some curve over here. And then at this knot, it changes potentially to a different curve under the restriction that we have continuity there. And then another curve that goes like this. To fit a spline, you need to say how many knots and how curvy can the curves be inside the knots. So if I say here are my 3 knots, what I'm going to do with the BS function is tell it about curviness through its degree argument. A spline of degree 1 is a line. If I said fit a B spline to these data with these 3 knots of degree 1, I would be fitting a connected line segments. If I increase the degrees of freedom to, say, 3, then I allow for there to be essentially a cubic polynomial inside each of these regions, with the restriction that they join and are continuous at the knots. So we might say the red curve is for degree equal 1, and the green curve is for degree equal 3. Yes?
So obviously if you increase the degrees, it's going to fit better and better. And how did you decide which degree you're going to go for?
So question is about how do you decide what degree to use? And the more wiggly you make it, the better it's going to reach out and fit the raw data. So that's a good question. Let me give a little spiel about model building. Okay, so if the goal, there's 2 kinds of inference that I want to speak about for just a second. When we do inference, let's say model-based inference, regression-based inference, there's a couple of different styles or flavors of inference. One is what's the term? Let's call it explanatory. And another is called predictive. Explanatory inference is like what we've been doing this semester. We have a response variable and we have some covariates. We want to ask, what's the effect of the covariate on the response? Give me a p-value for is there a treatment effect, for example. Give me a confidence interval on the change in mean associated with such something. If the goal is p-values and confidence intervals to answer a scientific question, a hypothesis test, for example, then we are doing what we're going to call explanatory inference. The goal with explanatory inference is to have a model that is suitably accurate and interpretable, and the goal is not to try to fit the data as perfectly as possible. If the goal is to ask, is there a treatment effect, for example, then I'm not interested in model selection things per se. So the way I recommend thinking about building a model when you're in this explanatory case is before you fit any models, do exploratory stuff, pictures. Draw a scatter plot of response versus the covariate. Does it look roughly linear? If so, go with a linear model. Using exploratory techniques, look at the effects of other covariates. Do these covariates appear to be relevant to explaining the response? And as much as possible, use pictures and basic summaries to guide your choice of model. And your goal should be, before I fit any models, just based on exploratory stuff, domain expertise, and my expectations given the experiment, I want one model. And ideally, I write this model down up front. Based on some pictures, some exploratory stuff, no p-values or any aggressive inference type things to guide this. Based on exploratory and domain expertise, prior expectation, I'm going to say, here's my model. It's the response equals beta 0 plus beta 1 treatment plus beta 2 gender and that kind of thing. So pick your model as, try to limit the amount you use the data or how aggressively you use the data to choose the model. The reason that I'm saying this is because at the end of the study, you did this experiment and you want to know, is there a treatment effect? Remember how inference is engineered to work. It's engineered to work like you go get a data set, you do one confidence interval, or you do one p-value. One p-value to answer one question is that's what the goal is. That's how we have correct interpretation of a p-value. If I do one experiment and I do one test, get one p-value, I can correctly say, I reject the null hypothesis at a type 1 error rate of alpha. But if instead you have a response variable and you have covariates x1, x2, ... xp, if instead, and our goal is still explanatory inference, what's the treatment effect? If we were to use some aggressive, algorithmic way of building the best fitting model, like let's try a spline with 3 degrees of freedom, then let's try a spline with 5 degrees of freedom, then let's try a cubic polynomial, then let's do this, let's try lots of different things. Maybe do that stepwise regression type of things where you let an algorithm automatically pick which covariates go in. If you take your data and do aggressive model selection, to get the best model. The problem is that squirrely arrow there is not going to be reflected in the inference that you do on your final model. So for example, suppose you do stepwise regression. That means the algorithm picks the single best covariate to add, and then it picks the single next best to add, and so on until it stops according to some criterion. So you aggressively built this model by looking at the data. Now, if you look at the coefficient for treatment effect, the p-value for that coefficient is not reliable anymore because you've used the data, you kind of overfit the data, essentially. When we want to explain a relationship, the ideal is to write down a model, fit that model, and do inference based on that model. Not fit 20 models and pick the one that looks best. When we do that kind of thing, kind of fishing around for a good fitting model, we are accumulating chances of making mistakes. So our error rates are higher than we would claim. It's kind of a subtle thing. When you take regression classes, they teach you stepwise regression. Seems like a sensible thing to do. You hear things like you want a parsimonious model. So if you have 20 covariates, maybe try 20 different models where you have some subsets of the covariates. You need to be careful when you're doing that, because the more you use like formal methods to choose what the model looks like, the less reliable your inference is at the end. I have a simulation that shows this. I'll see if I can find it. I'll see if I can find that. The other kind of inference is predictive inference. So this would be if I want to, say, predict pain score for somebody under a particular regimen, given gender and race and all that. Or I want to classify individuals in terms of a categorical variable. Do you have cancer or don't you? When we do predictive inference, when we build predictive models, this is where I think it's more relevant to do formal model selection. So when we do predictive inference, we often do some form of algorithmic model selection. But what we do to guard ourselves against this issue in the predictive setting is we use either cross-validation or a held-out test set to assess performance. And by doing those, one or the other of those, we will get a generalizable assessment of the accuracy of the model. For predictive purposes, the main goal is prediction. You want to predict accurately. But again, you don't want to overfit the data, because you don't just want to predict on your sample of observations. You want to be able to generalize it. So the way that we gauge that generalized accuracy is either with this resampling technique called cross-validation, or by having a held-out test set that was not used to build the model. Okay, so you asked about how do you choose the degrees, and what I would say, trying to stick with the theme that I was just discussing, I would say make pictures. So you could make spaghetti plots, for example. And you eyeball the spaghetti plot and you ask, what kind of curve does it look as needed to capture that, roughly speaking? Doesn't look linear. Maybe a little bit of a curve, maybe just a piecewise linear. So make pictures, I would say, make pictures. And then let me say that there are some optimality properties of a spline with 3 degrees of freedom. 3 is kind of a magic, not magic, but I mean it works really well for a wide variety of types of curves. So a cubic spline, that's like BS with degree 3, is I think the default for a lot of software. If you just ask for a spline, it'll give you a cubic spline. And there's theory that says cubic splines have some optimality properties for estimating arbitrary curves. So when in doubt, if you really need a curvy relationship, a cubic spline will probably be sufficient. I think you would want to argue for the simplest kind of curve that is sufficient. So if a cubic spline works, you don't need to worry about, say, a degree 4 or higher. Yeah, so I would make pictures, eyeball it, try to get a rough feel for just what's the nature of the pattern, and go from there. So just to reiterate, I would not recommend, if we're doing this explanatory inference, I would not recommend let's try a piecewise linear, and let's try a cubic spline, and let's try a degree 5. and pick the one that has the nicest looking results. That's inviting mistakes and overfitting. Is that okay? Yes?
In some piecewise situation, the data will not meet the loss. So can I also use the BS function?
Okay, so if we had cases where the functions were not expected to meet at the knots, you would need a different technique. So one simple technique could be a step function, where you allow an arbitrary, unconnected value in the different regions. That's easy to do. You could put a categorical variable into the model. That's essentially like a ANOVA right there. If you were to say response tilde a factor that was for each of these time periods, you would have a step function like this. I don't know of many cases where it's expected that you have some curve and then a totally different curve and then another one like that. I'd have to do some research on how to do that. But the splines will make things join up at the knots. So let's see how we can use these splines. I'm going to do linear regression, LM, and we've seen model matrices or like design matrices. We've said in our early regression coverage that we can write a regression model like y equal x beta plus epsilon, where x is called a design matrix or model matrix. Whoops, design matrix. If you have a design matrix, like suppose we said x is, there's a function called model.matrix. If we said model.matrix, age plus sex plus age times sex, like in the orthodont data, then capital X is going to be n by p, where p is the number of regression coefficients that correspond to this model. So it is that capital X at the top, the matrix that is used in representing the model. When you have one of those, you can fit the model by saying y tilde capital X. That's just another way of using LM. So you can say LM y tilde age plus sex plus age times sex. Or if you have a design matrix, you can just plug in the design matrix. LM knows how to work with both. So here, the highlighted command is of that form. It's saying y tilde a design matrix. BS is going to give us a design matrix. I'll show you what it looks like before we run the LM command. This is what BS returns when we ask for a piecewise linear function. So a B-spline is a fairly, it's kind of mathematically sophisticated what it's actually doing, so it's hard for me to show you exactly what these numbers are. But it is able to represent this piecewise linear model with just two coefficients. When I say BS x knots is 1, degree is 1, it gives me an n by p design matrix, n by 2 in this case. So this right here is essentially like that capital X design matrix that I was writing on the whiteboard. So I'm essentially using LM to fit a regression model with a specially prepared design matrix. Let's fit it and look at the output. One problem with using B-splines or splines is that the interpretation is harder. That first coefficient is not exactly it's not exactly a slope like we're used to thinking of it. It's when we work with splines, it's harder to interpret the model. But what we do have is a nice representation of the data that can be piecewise linear like this. So these are the fitted values of the model. And you can see that they are piecewise linear. If you wanted to ask, is there a time effect? Is there a time effect? Or is this flat? Is there no trend over time? We now have a regression model with a couple of coefficients that speak to time effect. So we know how to test whether those can be removed with either a likelihood ratio test or an f-test. So I could use the ANOVA function in R, that ANOVA function that does f-tests. I could fit this model, and I could fit the model with only the intercept and compare them with an f-test. So you now know how to fit a time course, and then you could ask, is there a time course? We could similarly allow for there to be a treatment variable. So suppose we had a treatment variable and we wanted to allow for a piecewise linear function for the control group and a separate piecewise linear function for the treatment group. We can do that as well. And then we could test using an f-test or a likelihood ratio test whether there's a difference in the time courses. So like in a genetic setting, we might have, I've seen a data set where we had time course data. For some gene, we have a number at multiple times for individuals with cancer and for individuals without cancer. So suppose we had 2 time courses. Our model has 2 separate time courses, one for the control group and one for the treatment group. Using splines, you can have this regression model that has that parameterization, and then you could test using likelihood ratio or f-tests whether these are different from each other. And that would be a test of whether the curves are different. Rather than going at a particular time point and doing like a 2-sample t-test, using these curvy models, nonlinear models, you can test, is the curve for the treatment group the same as the curve for the control group? Which is pretty handy. When you have time course data, that's kind of a natural thing to do. Ask whether the time courses are the same. In a 1-sample group, you might be interested in, is the time course flat? Is there any change over time? So here's a curve that we estimate, and we can test, is that flat or not? This right here does a piecewise linear fit. I said use 1 knot. So it was going, by default, it's going to find the best place to put the knot, and it was right there in the middle. And then degree 1 means do lines in the different regions that are defined by that knot, with the restriction that they connect in the middle. Now let's do a more flexible fit. Here is a cubic spline. So degree is 3 now. Still just 1 knot. Now I have that kind of pattern. So it's following the same basic pattern, but now it's allowed to be a cubic on the left and a cubic on the right, subject to there being continuity at the knot. Okay, so now let's look at a real data set and see how this might be interesting in practice. I'm going to look at these menarche data. So these are data from a prospective longitudinal study on body fat accretion for 162 girls in a particular study. We're interested in a time course. We're interested in changes in percent body fat before and after menarche. Menarche is when the menstrual cycle begins for these girls for the first time. Okay, so let's see. We have at the beginning of the study, all the girls were pre-menarcheal and non-obese. All girls were followed over time, so annual measurements until 4 years after menarche. At each examination, we have a response variable that is a measure of body fat. So we have a measure of body fat based on two different ways. I think the response is percent body fat. These data are time course data, but they are a little bit different from like the orthodont data. The orthodont data, we had 27 individuals and every single one was measured at the same 4 time points. Time 8 years, 10, 12, 14. For these data, we have 162 girls, but they were all measured at potentially different times. They come in annually until menarche sets in, and then 4 years after that. So we're going to have potentially different numbers of observations per subject depending on how quickly their menarche set in. What we have is an average of 6.4 measurements per subject. Time is going to be coded as time since menarche, and so it can be positive or negative because these girls were followed. They were all pre-menarche when the study started, and we watched them until menarche hit and then 4 years afterwards. So time is potentially negative. And then our variables are defined here. We have our identification variable that's critical with correlated data. We need some indicator for which observations go with the same individual. We have their current age, so at every observation of the girl we have their current age. We have their age at menarche and time and the response, percent body fat. So we're going to consider a regression model that says fat response is a function of time. Let's model the time course of fat for these women, for these girls. The data are not in CSV format, so I had to use a scan command. You can just use my code. But I'm reading in the data, and then I'm going to organize them into a data frame and define the column names. Let's have a look at the data. So we have 1,049 rows. We only have 162 girls though, so we have a lot of repeat measurements on the same girl. Here's the first few rows. First 6 observations are all on the first girl, ID 1. So she was initially measured at age 9.32. This was 3.87 years before menarche set in and her percent body fat at that time was 7.94. So then we saw her 3 more times prior to menarche, and then at the next one, it had kicked in. So I wonder how many observations. Let's do table data $ID. Let's see how many observations we have per girl. The first girl, we have 6 observations. The second one, we have 9, 8, and so on. And their ages are going to be different. These are all arbitrary ages. It's not like the orthodont data with 8, 10, 12, 14 for every individual. That's okay, though. These splines are able to accommodate unequally spaced and unequal numbers of time points for individuals. So it's not a problem at all for GEE and splines. Okay, so let's try a GEE model that treats time as a cubic polynomial or a cubic spline. I didn't specify the knots. I didn't tell it how many knots to use. BS is able to pick the number of knots automatically using some rules of thumb. So I usually just let it do that, pick the number of knots. So this is the way we use GEE, and then it's a model statement like we've been doing with regression. I have to tell it the ID variable because we're doing correlated data. And remember, the other thing we have to do with GEE is specify a correlation structure to use at least to begin with. In the lecture videos, I've said that GEE is, one of its nice features is, just like GLS, you can specify a structure, compound symmetric or unstructured, that type of thing. With GLS, if you specify a structure, that's the structure that's going to be used. The model is going to be fit, assuming that, and it's going to be explicitly used in the model fitting. Oh, we're out of time. Okay, sorry. Let me just show the picture. I'll revisit this next time. Fitting this model. Okay, so we have response versus time, and we fit a regression model that allows for correlation and also allows for a curvy time course. So I'll say just a little bit more about correlated data on Friday, but we're about ready to move to our next chunk of material, which will be survival data. Biostatistics, one of the early applications was survival data, like how long do you survive after diagnosis with cancer? And the challenge is sometimes people drop out of the study. So I know you lived at least 9 months, but I don't know how long exactly. Should I throw your data out? No. Should I say you died at 9 months? No. You need something else. That's survival analysis. Okay, thank you. See you Friday.